period 7. I hope you enjoyed your 2 blocks at Wallops when you were not learning math. Period 8, how many blocks were you of math were you at Wallops for?
1.
Just 1. Yeah, good. So that's why you're going to have this fun live educational experience, but we're going to make this watching at home on video educational experience also fun for you. We have a room full of wonderful people. Hopefully they will not appear on camera, and hopefully we won't have to scream at them because we don't want to do that. Good. Like I was saying in the intro that happened before I hit record, we know how to figure out when functions are increasing and decreasing now. Therefore, we can solve optimization problems. Now, off screen, before I hit record, everyone groaned really, really loudly for some reason. Why? Where did the groan come from? Because you did this in pre-calc A? Is that why? Is that where the groan's coming from? Yeah. Good. That's right. There's this whole week or something in pre-calc A when you solve these so-called quadratic optimization problems, and students generally consider this to be sort of hard. But one nice thing about learning is sometimes you actually get smarter, and sometimes if you go back to something that you used to think was hard, then magically it's easy again, and then you feel good about yourself. For example, let's solve an optimization problem right now. Suppose you have so let's just call this problem number 1. Suppose you have 200 meters of fencing. Also, it is considered traditional. If you go to like an Algebra 1 textbook from like 30 years ago, they would make all their examples about like farms and like cattle and stuff like that, because just like once upon a time, 50% of the country was like rural or something like that. I have never done anything with cows. But let's just go with the flow and say that we have 200 meters of fencing. And what we would like to do is enclose a rectangular section of grass for our cows to graze in. And of course, we want the cows to have as much grass as possible, because then they'll be happy, So, question, what shape should we make our rectangular fencing in order for our 200 meters of fencing to enclose the largest possible area? Alex, a square. Yeah, so this is a question that you can pose to a first grader probably, and they'll still know the answer. Should you make a long, skinny rectangle like this? No. In fact, it turns out, and one can prove this, I'm going to skip the proof for now, that the best, so to speak, the best rectangular enclosure is the one which is a square. By the way, this generalizes to any polygon. If you insist on the enclosure being triangular, and you have a certain amount of perimeter, then what shape triangle do you think will produce the largest area triangle? Equilateral triangle, yeah. And this holds for every side. So if you have a pentagon, it is always the regular pentagon which maximizes the area for a given perimeter. Is everybody with me? This is called the isoparametric theorem. It says that for any polygon at any number of sides, it is the regular polygon which makes the area the largest for a fixed perimeter. And conversely, if I were to take the same square problem and say to you, I want the rectangle to enclose a certain specific amount of area, what is the shape that will do it with the minimum amount of perimeter? I'll say that one more time. I'm going to build a rectangular enclosure, but I want that rectangular enclosure to have a certain specific area. What shape should I choose so that the perimeter is minimized? Square. Also square. So square is the solution to 2 problems at once. It's the solution, it's the rectangle with the biggest area for a fixed perimeter, and it's the rectangle with the minimum perimeter for a fixed area. And this holds for all the other things I said as well, to triangle and pentagon, etc. Also, it's true that for any particular shape, say square, the hexagon does a better job, so to speak. So the ratio between the area and the perimeter gets better with the pentagon than it is for a square. You can get more area for a given perimeter. And of course, if you take this all the way, says Adam, in the limit, the actual 2-dimensional shape, which gives you the most area for a given perimeter, would be the circle. Yeah, and in 3 dimensions, if you take this up a dimension to 3 dimensions, what is the shape which gives you the most volume for a given surface area? Sphere. A sphere. Yeah, and they're all sorts of facts about physics, which are the kind of a result of these math facts. So the reason why soap bubbles are spheres, for example, is because it's the most stable shape. It gives you, it sort of minimizes the surface area. Okay, good. Let's do a problem that's a little bit harder though. Ready? Here is a little bit harder problem, but still easy enough that a ninth grader could do it. Now suppose we have 200 meters of fencing, but there also happens to be a river. And so we get to use the river. Now here is the river. I'll draw it in. Do you want this to be a regular river or something more horror movie? Snake. Anything? Anybody else?
Piranhas.
Piranhas. How do I spell piranha? Piranha.
Alligators.
Clowns. Okay, good. This is a good time to confront your fears. What's the other one? Crocodiles. Okay, good. All right, so I ran out of space, so I'm going to stop there. Here we have a snake, piranha, clown, croc river. And this is pretty scary. Therefore, if I was a cow, there's no way I would go in such a river, true? Yeah. Therefore, does everyone see that we get to use the river as like one of the sides of our rectangle? Yeah. Okay, so now the question is, I have 200 meters of fencing. I am going to build a rectangular enclosure. What are the dimensions of the rectangular enclosure that I should build in order to get the maximum amount of area? So it's the same as question 1, but now I get to use the river. Okay, first of all, just blurt out like what you think might be an answer. 200 over 3, says Soren, which, in other words, what is Soren saying? Make a square, right? Okay, Soren says make a square. No. Other people are saying no. Even people at his own table are turning on him, people at home. Okay, wait, no, don't say anything. We're just going to do it. We're just going to be ninth graders. Ready? Say ready. Okay, so these optimization problems, the reason why students always love them is because they involve like reading, thinking, picking variables, and all that kind of good stuff that involves like real, mathematical reasoning. So what we need to do is like draw a rectangle. So let's draw a rectangle. What should it look like? I'll just draw it kind of like this with no particular dimensions in mind, just not to spoil it or anything. So of course, what we want to do is we want to maximize the area. Maximize the area. So therefore, what is the thing that we are trying to maximize? The area. Okay, yeah, good. So all right, good. So I'll just write that again, I guess. We want to maximize the area. Okay, so I need like a formula or like a function. X times y. Okay, so anyone who's saying x, y, you seem to already be deciding that we should choose some variables x and y, which is extremely reasonable. Let's call this like x because it's horizontal, and we'll call this y because it's like vertical as viewed from above or something like that. And wait, table, you guys good? Yeah. Okay, so now that we've chosen variables, in other words, let y be the length of the side of the rectangle in the direction perpendicular to the Clown River, and let x be the length of the side of the rectangle that's parallel to the Piranha Snake River. Okay, so what's the area? It's just x times y. Okay, and what we want to do is make x times y as large as possible. Okay, but we have like 2 variables or something, right? So that's kind of weird because we have like a, multivariable equation or something. Or do we?
X plus y plus x something equals 200.
Yeah, but try that again.
2y plus x plus 2x.
Yeah, and he says it's not true that x and y are unrelated to each other. In fact, they are related because, okay, wait. Small thing that's so obvious that it's almost not worth mentioning, but I'll mention it anyway. You should probably use all your fencing. Because if you don't use all your fencing, you have not made the biggest possible rectangle, agreed? Because if you had a little bit of fencing left over, you could just get a little bit bigger and better. Therefore, I think we can claim that the optimum solution is going to use all the fencing, and therefore, class, 2y plus x equals 200. Yeah, so true. Okay, well in that case, then there is a relationship between x and y, so I can rewrite this equation in terms of just one variable. Which variable do you want to use? X. People like x because it's like, good or something. Or wait, you want the final, what do you want? What do you want to do?
Use y.
Like solve for y? Solve for x?
Solve for y.
Solve for x.
Oh my god.
Okay, we solve for x. X is 200 minus 2y, that's a fact. And therefore, we go and stick that in over here. And what we end up with is the equation a equals 200 minus 2y times y. True? Oh, this is still stuff you did. You did problems like this exactly in 9th grade. Actually did even harder problems than this. So what do we have here? What we have now just sort of made is an equation, 200y minus 2y squared. And what this equation does is takes as input a y value and it outputs the area. Cool? Okay, and so now what do we want to do with this function? Graph it is what you did back in is what you did in 9th grade. We want to optimize it, right? We want to, in fact, what we want to do is maximize it. So okay, so I can think of two ways to do this. There's the 9th grader way. The 9th grader way is to say, all right, this is a quadratic. I know everything about quadratics. Let's just like, actually I can think of three ways. One way is to just graph it. So I'll take that suggestion first because I like that suggestion. So if we graph it, then what do we get? Well, we get -2 times, or -2y, in fact, I can factor out of both terms. If I factor a -2 out of -2y squared, I'm left with y minus 100, right? Have we done that correctly? We have. Okay, and so, of course, what does this quadratic look like then? Here we have like the y-axis down here, and we have like the a-axis up here. It's an upside down quadratic with a root at 0 and a root at 100. And therefore the vertex of the parabola is in the middle, and it's upside down, and therefore this is 50. Okay, so does everybody agree that based on like Algebra 1 knowledge, I know how to graph this upside down quadratic? It factors nicely, the roots are where they are, the vertex is halfway between. It must be true that when y equals 50, this thing is the smallest. Okay, so by the way, okay, let's call this 8th grader. This is what an 8th grader would do. What might well, whatever. This is certainly one good way to do it. Are there other ways? I had a way, and then, oh yeah, that was the other way I was thinking of. The other way I was thinking of was you could put it in, you could complete the square. Yeah, probably no one wants to do this, but I'll just do it for you. You could take this, you could factor out a -2, giving you y squared minus 100 y. And then half of 100 is 50. So then you like stick like 50 squared in there. I think I'm doing this right. And then what did we really just do? So 50 squared is like 2,500, I guess. But I really just subtracted 5,000. So I need to add 5,000. I'm probably doing this all correctly. And therefore, what is this? This parabola becomes the parabola -2 y minus 50 squared plus 5,000. And having completed the square and put it in vertex form, I now can tell you where the vertex is. And the vertex is up here at 50 comma 5,000. True? Okay, so of course we're getting the same answer, which is that the peak is at y equals 50. And maybe now is a good time to talk about the fact that Soren was wrong after all. Because when y is 50, what is x?
100.
Yeah, if y is 50, then x is 100. And if we trust all this math, and we should, then it has turned out that the best possible rectangle is the one, and maybe this is surprising, maybe not in retrospect, is the one in which this is 50 and this is 50 and this is 100. Okay, would someone like to explain sort of intuitively why this is actually not surprising and in fact predictable? So Soren just guessed square, and that's kind of what I wanted someone to do, which is just to guess square without thinking about it too much. But, and this is something called becoming smarter, if you have an intuition and your intuition is wrong, then that means it's a learning opportunity to get the right answer, to meditate upon the problem, and then to develop a more strong intuition. So looking back, we'll just let Soren answer since it was his wrong initial intuition. What's your new intuition?
By making X bigger, you're using half as much, like fencing as if you make Y bigger. So X should then be larger, and then you maximize the amount of room you can use in that situation.
Anyone else? I feel like we could do that a little bit better. Yeah, Victoria.
I feel like we just got a square and got one of the side lines of the square that we didn't use and added it to one of our lines.
Yeah, she's saying it's kind of like there is a square in a way, but the square got broken apart or something and turned into, it's like there was a square and then, what happened here? It's like there was a square, says Victoria, and then we broke off, we realized after building the square that we didn't need this pink side because there was a river there. So we broke the pink side off and moved it over here and we got like an extra 50, and so we used it to make our thing twice. Is that kind of what you were getting at? Okay, maybe just what Soren said was pretty good, but maybe it just can be made a little bit better. The intuition here, why you could have just come up with this answer actually on the spot, is, well, you get a river side for free. And so in some ways, every meter of fencing that you spend working on this direction, the direction perpendicular to the river, you have to pay double for. Whereas, that is what Soren kind of said, but his explanation was pretty good. I just think it could have been a little bit better. Whereas, because the river is there, you get a side for free. And so this side of the fence costs half as much, so to speak, as this side. You think that's exactly what you said?
That's exactly what he said.
It's basically what he said. The same words.
Let the record show that everyone believes. We'll check the video that Soren said exactly this. Okay, if you did, great. All right, good. What does this have to do? What's missing from this board? Calculus. Suppose you knew calculus. Could you do this problem with calculus? Yes, you could, because you could just go to the same exact point where you have that a equals 200y minus 2y squared, and what could we do? Take the derivative. Yeah, we just take the derivative. What's the derivative of a with respect to y? 200 minus 4y. And what do I do with this derivative? Find where it's 0. I can do that by factoring out a negative 4. If I factor out a negative 4, I get like y minus 50, something like that. True? Okay, and now I'm going to make a sign chart for the derivative. What is the sign chart for this derivative? It's a line, but it's a line with slope negative 4. So it starts high and then goes low. True, true? Yeah, so it's plus minus. And therefore, what do we know about the function, the a function?
It's increasing.
It's increasing up until 50 and it's decreasing after. So by the first derivative test, there is a relative max at x equals 50. I'll even just write that down just for review. Since, this is what we did last class, since a prime changes from positive to negative at y equals 50, a has a relative max at y equals 50 by the first derivative test. Okay, cool? Okay, so in here it was a little bit overkill to use calculus to solve this problem because, dude, it was just a quadratic, so we didn't really need calculus, get it? However, maybe are you now realizing that this technique of finding the roots of polynomials means that we can now solve any optimization problem, ones which even involve functions that a ninth grader could not maximize. Basically anything other than quadratic we would need calculus for. Okay, good? All right, let's go. I got a problem for you. We are going to make an oil can. Okay, and we are going to make a cylindrical oil can. A cylindrical oil can with volume 1 liter, which is also 1,000 cubic centimeters. Okay, yes?
The camera can't see that.
Oh, that's a good point.
So, Alex,
Hey, thank you.
Hey, how's it going?
What's happening in math so important we got a videotape?
So many things, you have no
When I say
idea.
Videotape, obviously that's old technology.
Yeah, this, actually, no, I have moved on to using my iPhone instead of that 10-year-old video camera I had. It still worked great, but it no longer charged. So that's kind of a problem. The power cords are the things that always get you.
Yes. I'm sorry for that.
Yeah.
You have it squarely focused on this blank.
Not really, I'm not trying very hard. It's kind of a,
Just in general in teaching, not trying very hard.
yeah, good.
I need to see some, I need to see Samantha here today.
No.
She's on a field trip.
There's a field trip today?
Yeah.
For real, I know. You should probably yeah, exactly. All right, good. Cylindrical oil can with volume 1 liter. Okay, so we're like a company. We're gonna make some oil cans. All right, guys, let's think. What kind of shape? Oh, I already said cylinders. What are good things about cylinders and what are bad things about cylinders? Why might you want your oil cans to be cylindrical, and why might you not want them to be cylindrical? Okay, I'll take say one thing.
you can roll them around.
Okay, that's like a not terrible idea, right? That's why, beer kegs are in the shape of cylinders, and like wine jugs once upon a time and even still are in the shape of cylinders. The nice thing about an oil can is you can roll it around, so that's like good, I guess. What's bad about a cylinder?
It rolls around.
It rolls around. Maybe you don't want it to roll around, but if you don't want it to roll around, you can just go choop,
Yeah,
and then it's
exactly.
okay.
So
So that's
you
kind
don't
of
make
best
it-
of both worlds, right? That's the great thing about a cylinder. If you don't want it to roll, you just put it with the circle down. We're learning a lot of things about shapes today. And if you do want it to roll, you put it, circle on pointing onto the sides, and then it rolls. Seems great. What could possibly be bad about a cylinder? Yeah.
You're not maximizing area by using this. Volume by using this.
You're not maximizing volume. Okay, that is true. However, if our goal was to maximize the volume for a given amount of material, you're worried about like the material, then what shape would our cylinders be? Spheres. You will not see a lot of spherical oil cans being sold in the market because that is a sucky shape to have your oil can be because then it is always rolling. This is some good conversation going on here. Okay, good. So, all right. So good. So Adam is kind of on the right track, which is he's worried about the materials to construct the can being very expensive. Let us in fact pretend that the materials to hold this oil can are very expensive. So we actually are interested in minimizing the surface area. Yeah? Okay, but suppose you weren't worried about that. Does anyone have any just last minute like aesthetic things about what if you were going to design an oil can, what shape would you want it to be and why? Still recording? No. But it has to be a cylinder. But you still have some choices. Like what kind of cylinder?
Like a tall cylinder.
I want it to be a fat one.
Like so you have different kinds of cylinders, guys. You have cylinders that look like this. Would this be a good shape? Would this be a good shape for a cylindrical oil can? Why yes or why no?
Yes, it's
Too tall. What's wrong with this? What's wrong with it being too tall?
gonna hit somebody.
Okay, it could fall down. It could fall. It doesn't fit in like cabinets and stuff. That's more where I'm going with this. Yeah.
What comes in a can?
Oh, this is like cooking oil. I was thinking, not like petroleum. But really, it doesn't matter what. Because 1 liter. I guess 1 liter is kind of big.
Oil come in a can.
like from Italy, I feel like you get your oil, like you would be like your olive oil comes in like an aluminum cylinder.
No, but I know exactly what that's.
Yeah, good. Alright, got him. Glad we're having so much fun today. Okay, so yeah, anyway, this would be really hard. It would be hard to like, you just wouldn't, well, this would be bad. But conversely, would you want your oil can, which we now know to be cooking oil, to be shaped like this? What's wrong with that?
You can't roll the stack.
Easy to stack, but
Hard to roll.
hard to roll. I don't know if there's gonna be so much rolling going on, because 1 liter I can carry that pretty much fine. Pouring is gonna be not so much fun. You could just open it up like a sardine can and dip into the top. No, I don't think you want to
Then
do.
you could just take like the crumbs.
You'll get a lot of crumbs in your oil can. All right, good. These are good conversations. All right, so as it turns out, we will ignore all those aesthetic concerns and we will focus on one sort of unambiguous mathematical properties. What we want to do is minimize surface area. Okay, good. Which is kind of like what Adam was talking about. All right, so what is the surface area of a cylinder? Something every 5th grader should know because it's really that easy. Just throwing in some insults there.
Power squared plus 8.
Pi r h.
Pi r squared H. Yeah, who said 2 pi r, bro? Who said 2 pi r?
That's the volume.
Who said 2 pi r?
Okay, so good. It is true that the volume is the area of the base times the height. So wait, but that is also relevant, so we can just write that down. Pi r squared h. But the surface area, what is the surface area? Circle up. The yup. If you unfold it, then you get like circle, and then you get like rectangle, and like circle, yeah? And the rectangle's height is the height h, and then the length of that rectangle is 2 pi r, the circumference of the circle. Is everyone feeling this? All right, good. So what is the formula for surface area? Answer.
2 pi r h.
2 pi r h is the lateral surface area.
Plus.
You were not gonna say that. You were not gonna
All right. Good job. All right, is everyone feeling good? Good. Okay, so wait. Now stop talking to period 8. Love you guys so much. Good. So anyway, what are we doing again? We're trying to minimize. We're trying to minimize the surface area. Therefore, I should write a function for the surface area. What is the surface area? Oh, it's that. Okay, I can write that down one more time on the top of the board. 2 pi r h plus 2 pi r squared. Looking good. However, I have 2 variables. So once again, I'm in like a bad position. Raj, you agree?
Yeah.
Are these 2 variables truly independent of each other?
Yes. Kinda.
No, not. Because our cylindrical oil can has a fixed volume. So the bigger I make the height, the smaller the radius will be. And the smaller, right? The bigger I make the radius, the smaller the height will be. Therefore, this is exactly analogous to what we just did. What's up? We're videotaping class. We're also like screwing around like a lot today. Yo.
They're teaching us to come in.
I know, it's very popular, this spot. It's very, I should get more teachers should come and bring me like a cup of coffee or like a cookie.
offer espresso. He asked if we wanted espresso.
Did I just not hear him?
Yeah. I was gonna say something. I don't want to say something.
Did he offer and he spoke to me?
Yes.
Was it obvious to you that
want espresso.
was it obvious to you that I didn't hear him?
Yeah.
Okay, anyway, no time for that now. Good. Wait, class, wake up. Wait, we gotta kind of, we're screwing around too much. Yeah, I know. So wait, go, talk, fast, more. What next? What do we do?
1,000 equals pi r raised to pi r squared.
The volume is pi r squared h, but it's equal to 1,000. Yeah, because you have to. If you said 1, that would be a units mistake. Because yes, the volume is 1 liter, but the volume formula assumes that your R and H have a certain units of being like centimeters, so you need to go for like the, you know what I'm saying? Okay, good. So whoever just pointed that out, good job, Eric, or whoever it was, I can't remember. The volume is pi r squared h, which is 1,000. Therefore, you got to solve for one variable. Which variable do you feel like solving for? H. Good. So the people have spoken, and what the people want to do is say that h is 1,000 over pi r squared. True? And what are we going to do with that? Stick it into the other formula, and well, what happens now? What do I get? I get 2 pi r. H is now 1,000 over pi r squared plus 2 pi r squared.
If I get to have you analysis too, when we get to optimization and I say, hey, you remember doing these problems? Remember this day.
I mentioned optimization like 30 minutes ago, and they all went, oh, and they groaned. So you better groan. You groan for him too. All right, good. Wait, let's keep going. We've used up all of our screwing around budget plus more. So now we're gonna get serious. Pi's cancel. Yup. So this is 2,000 over r plus 2 pi r squared. And what have we now done? Putting in a whole bunch of work. What we now have is a formula which takes as input a radius and output the surface area. I'm calling that function S for surface area, and I'm writing it explicitly as a function of R. And of course, this depends on the fact that I've built into the problem that the volume is fixed. Cool? Okay, now, this formula is looking kind of complicated, y'all. So you cannot do this if you are a 9th grader, because this is not a quadratic. But we are not scared of this function because we can optimize, and we can find the relative extrema of any function as long as we can differentiate it and make a sign chart for the derivative. Then we can do an analysis and we can, cool? Okay, good. So it's time. So far we've done no calculus. All we've done is like geometry, a little bit of a struggle, a little bit of algebra, and now we're ready to take the derivative. Are you ready?
Yep.
Let's go. Valerie says differentiate. What do we get? We got like S prime R, I guess.
It's negative 2,000.
Careful. This is 2,000 r to the negative 1. So that's going to be negative 2,000 r to the negative 2. And then this will be plus 4 pi r. Okay, that took about 1 second. So that was kind of nice. Now what? But now I have to do a bunch of like tricky algebra to like bring some. Yeah, so what should we do? Yeah, that is the smooth way to do it. Valerie says, I want to get this r to the negative 2 just right out of there. This is kind of like in line with what we've been doing, and we can also take out a 4. So she says factor out a 4r to the negative 2. If you do that, then what do you get over here? You get pi r cubed. True? And then this is going to be minus 500.
It's actually over for me.
Minus 500. Who's good? In fact, I will also factor out a pi because I just kind of want that like out of there. And this is what I will end up with. I will end up with 4 pi times r cubed minus 500 over pi. A little bit gross, but this is still the good thing to do over r squared. Wait, come on, you're good? The pi, yep, I think you're good. You multiply through, you get 4 pi r. Check, check. And when you multiply 4r to the negative 2 through by the negative 500, you get negative 2,000 r to the negative 2. when you take the pi out, it's just like, good. Okay, and then put that. All right, this is the professional way to do this because now I have this nice factored derivative, and we're pretty much done, right? Now let's make a sign chart for S prime. What does the sign chart look like? Denominator always positive. Numerator. Yeah, this is just like a x cubed function that got moved down, right? So it's only going to cross the x-axis once, and it's going to cross the x-axis at at cube root 500 over pi. It is a little bit of an ugly number, and it's going to change sign from what to what? Negative to positive. And therefore, what do we know? We know that my surface area function is decreasing and then increasing. And so by the first derivative test, S has a relative minimum at R equals the cube root of 500 over pi. Okay. Sounds like some people are, not like happy about that or something. Okay, you're allowed to be not happy because this number's kind of gross, right? And the reason why this number's kind of gross is because we were doing this proof like with numbers instead of doing it in general. So sometimes if you do it in general, you get like happy formulas where you feel like you really learned something. So there's a way to do this that's more cool, but I have to remember how to do it. Oh yeah, I remember now. Do I, though? I do. 4 pi r, yeah, boom, but then we get this, then we get the 4 pi r, yeah. 4, yeah. Okay, right, so right here, after differentiating, this is my OR. My OR says, if we wanted to be a little bit more cool, we could say, all right, take it from this point, where we learned that the derivative of S with respect to R was 4 pi R minus 2,000 over R squared, yeah? And let's use the fact that this 2,000 is really just 2 times the volume. In other words, let me just rewrite this as ds dr is 4 pi R minus 2 over R squared times 1,000. But 1,000 is just kind of like the number that's specific to this particular problem, right? So if we wanted to be a little bit smarter now, we would rewrite this 1,000 with what it really is. What is this 1,000 really? It's the volume. It's pi R squared H. Okay? So this becomes 4 pi R minus 2 over R squared times, in place of 1,000 I write pi R squared H, as these are just the same thing. Who's with me? Okay, the squareds cancel, says Valerie, and so this time I'm really learning something. What am I learning? The derivative of the surface area with respect to the radius is 4 pi R minus 2 pi H. Take out a 2 pi, and if I take out a 2 pi, I'm left with 2R minus H. And so, the real answer to this problem is that the surface area is minimum when
When R equals H divided by 2.
when H is 2R. And this is kind of like a deep sort of fact about cylinders. And if you think about it, it's in retrospect very reasonable, right? If you want someone want to phrase this in even a slightly different way. Bless you. Yeah.
is that each time you expand the R, you have to pay it twice because you have to, it's like, oh, you also have to pay for the surface area on the top of the cylinder and on the bottom of the cylinder.
Okay, wait. You might be doing something deeper, right? Even simpler. What is 2R? The diameter. Yeah, so what are the two things that are supposed to be like the same? This just like feels right. You might be doing something deeper, I'm not really sure. But the diameter equals the height. Yeah, the takeaway here is that the best cylinder is the one that's the most sphere-like, kind of like squat and compact and symmetrical. And so this is actually very unsurprising in a kind of way that's a little bit informal, that the best cylinder, the one which gives you the minimum surface area for a given volume, is the cylinder that is as sphere-like as you can get. So as like symmetrical, squat, compact, however you want to think about it. It's the one in which the height is the same as the diameter. Okay, yeah, question?
It's like a square if you look at it, right?
Yeah, and he says it's kind of like one which is a square. If you close one eye and you get rid of your depth perception, I think that is actually a deep observation, right? Do you see what he's saying? From the perspective of like fitting the cylinder through like a cut hole in the wall or something like that, it would be a square hole in the wall that would exactly fit if you were to slide the cylinder through. So in some ways, it is the like 3D version of the squaring kind of phenomenon being seen here. Okay, good. Woo, good. That finishes this introduction. I normally do this like 3 times as fast, but hopefully we had some fun. What do we have left? 35 minutes? Perfect. Let's do some
Chit chat.
curves.